Okay, before I get started, I'd like to thank these guys for putting on this this show. I've had to do this kind of thing before, and God, it's a lot of work. And then I'd like to thank Cool Essence for sponsoring the work, and special thanks to Matt and Rick and my brother Jim for encouraging me through the decade that it's taken to get this far. I haven't come forward before because there were so many questions unanswered. I think I've answered them, at least in my mind. And if you're interested in any of this, go to, whoops. I recommend Feynman's thesis. It's like $10 on Amazon, so cost is no object. That's $10 on Amazon. These are both great approaches to quantum mechanics. It's not the Schrodinger equation approach. I highly recommend them. They're both by Feynman. All right, well, I've got a little wager with Matt, and he says I can't finish this in 20 minutes. So, there you go. You guys, we'll see how we do. All right, so what we want to talk about is two neutrons and an electron. That's it. I'm not going to get into solid state or anything else. Behavior is determined by the electrostatic force. That's it. No spins or anything crazy. And it's described by quantum mechanics. All right. All the properties are predicted by the Schrodinger equation for molecular deuterium. It's modeled with atomic wave functions, and the bond is due to exchange energy. It's not a classical thing. And you use the Bornoppenheimer equation, you have to use it to solve this, and that freezes the nuclei while you calculate the electron wave function. All chemistry is based on this. They start there, and that's it. Okay. So that approximation is probably a good place to look to see if there's something wrong. And with the Fleischmann-Pons effect, would seem to require high kinetic energy deuterons, I think.
No.
And the reason for that is you need to localize the two. If they're going to react, they're going to have to be close together, and you're going to need to overcome the Coulomb repulsion, and that's going to require high kinetic energy. Plus, if you have the deuterons, if you have the deuterons and the electrons with about the same energy, they can couple quite easily. So there's a bunch of things. So you can't use a Born-Oppenheimer approximation, so what the hell do you do? Well, back in 1932, Dirac published an article. It's the one that encouraged Feynman to take the path integral approach. And he said in this article, he says, now there's an alternative formulation for classical dynamics provided by the Lagrangian, and we'll get into that in a minute. And there are reasons for believing that the Lagrangian one is the more fundamental. And he goes on to say, in the same paper, the Lagrangian method allows one to collect together all the equations of motion and express them as a stationary property of a certain action function. And there's no corresponding action principle in terms of the coordinates, momentum, or the Hamiltonian theory. All right, what the hell does that mean? Well, the action integral accounts for particle behavior over a period of time, or period of an observation. And the Hamiltonian is a differential equation. And so it has a hard time correlating interference effects over periods of time and space. So what that means is you shouldn't use the Born-Oppenheimer equation if you think that the kinetic energy of the deuterons is going to be high. So could there be another form of D2? Well, I think there is. My hypothesis is there's a correlated state of the two deuterons and electron that I call the linear momentum state. And it's a dynamic correlation obscured by the Born-Oppenheimer approximation. And basically what it is, it's an oscillation of the electron back and forth like that. I brought a visual aid here. If you think about the regular molecular deuterium, the electron oscillates around the nuclei like that. It just jumps from one to the other, and that's the bond. You can see it's not a very good bond. Okay, so in this particular configuration, you get basically the electron is doing that. So you can see it's going to be a lot better bond. All right, So let's see what we need. If this bond is real, then at least do the three miracles quite easily. The Coulomb barrier penetration, because the bond is 30 keV. There's no neutrons because the electron and nuclei are coupled. It's a textbook time-dependent coupled two-state problem. It's really, this stuff ends up being the easy stuff. You get a little bit of tritium, parts per million, because of the mechanism. And you also have orders of magnitude of effective bonding. You can go all the way from the Fermi scale all the way up to the just sub-angstrom scale. And that allows you to go from chemistry to the chemistry in the Fermi region. So it allows for a mechanism. But the nagging question is the linear momentum state, is that derived? Or is this just my fantasy? And for 10 years it was my fantasy. I spent a lot of time doing all this stuff, and I almost quit because I couldn't figure out whether you could justify that state. And it turns out you can. And it took me a while to find Feynman's writings, but we need three basic concepts to understand this. And you're going to have to bear with me because I got to show you the concepts in order so you'll understand why this thing works. And the action integral Lagrangian is something we need. And we're going to have to go through the path amplitude summation. This kind of cute way that Feynman discovered to demonstrate that, and then show stationary state requirements. It all comes together to show you that, wow, this really does work. And what we're going to have to do, I'll show you the what I call the D2 star. That's my name for this linear momentum state. And it's a classical bond, okay, and we're going to need that. We're going to review the double slit interference. You've all seen that before. I'm going to introduce Dirac's path amplitude and the principle of least action. We'll have some examples of that, some complex amplitudes, just to show you how Feynman explains this. And we'll have show you the stationary state requirements, and the conclusion will be that there's a semi-classical linear momentum state. So, what this is a graph of, these are the, it's a classical simulation just using F equals ma, right? This is physics 1A and calculus 1A, basically. It's three coupled second order difference equations. All it is, F equals ma for the three particles. The F is the electrostatic force. You just start with initial velocity of 0, line the particles up. In this case, they're 300 Fermi apart. The two deuterons are electrons, about 250 from the center of mass. You just start the simulation. The deuterons will oscillate against each other. That's the radial oscillations. This is time along here. And the electron, obviously, it's going so fast it doesn't graph well there. But if you stretch it out by a couple orders of magnitude, you can see the electron oscillation back and forth through the deuterons. And you have to model, of course, the potential through the deuteron, which isn't terribly difficult. All right, and if you draw a picture of it, it looks something like that. There's the deuterons oscillating against each other, and there's the electron that oscillates back and forth through the deuterons. And the dimensions will be determined just like the dimensions of hydrogen by the quantum mechanics. Because you can make the dimensions classically anything you want, just like the hydrogen electron. You can make it classically anything you want. And the electron is just acting like the force-carrying particle in nuclear physics. So the chemists aren't used to this kind of stuff. Okay, well, this is where quantum mechanics starts a little bit. We'll start with, this is right out of Feynman's book. You have electron source, double slits, and a detector. We're going to have two paths, path 1 and path 2. And to do the experiments, you're going to get an interference pattern with both slits open, and a diffraction pattern with either of the two slits open. You add the two diffraction patterns, of course, it's not the same. That's quantum mechanics right there. It's pretty straightforward. And you can use Dirac's contact transformation, which is in that same article that I mentioned before. And the amplitude for each of the paths is just calculated by the action. All right, and the action is equal the integral of Lagrangian, and Lagrangian is the kinetic energy minus the potential energy. Those are all classical ideas, and this is where classical mechanics meets wave mechanics. Okay, and you can see better on the next slide what the wave mechanics is all about. Again, this is out of Feynman's book. There's that same path, and you can look at it as waves, but the waves they're amplitude waves. They aren't real. They're a mathematical device. And if you use Euler's formula, you can see where the waves come from. This is an identity, and so that's just the cosine of the action plus the I sine of the action. That's the wave, and you can calculate this if you normalize it and all and square the sum of the two amplitudes. Okay, so Feynman's wave equation basically takes that idea, you got two paths, and you multiply it by this contact transformation, is what Dirac calls it, and you sum all the paths. In this case, there's only two. It's not too hard. We call it that's what the action is. But what we want to do, we want an infinite number of paths, right? Because we don't have a slits in our D2 molecule. So we need to be able to calculate an infinite number of paths. And it's more complicated than that, but we're simplifying this to make some sense of it. And you can solve this, actually, for the D2 molecule. But we're going to kind of take a conceptual approach today, and it's kind of fun, actually. So, okay. First of all, we need to know what the principle of least action is. I didn't know what it was before I read Feynman. And again, Lagrangian kinetic energy minus potential energy. 1/2 mv squared minus the potential. We do example here. Free particle, no potential. So we just have a particle that goes from A to B, constant velocity. That's it. It's very simple as you can get. Time A, time B. We're going to calculate the action. So that's the action of the classical path. All right. So it's just 1/2 mv squared times delta t. That'll be the action. It's fairly straightforward. But now we need the action for all these non-classical paths. I know that sounds weird, but that's what you have to do. That's the way the real world works. And you think double slit, all right? But we're going to want infinite slits. So we're going to have to let delta y vary. And so we're going to have these are all the non-classical actions, and we let delta y vary. We want to graph this, so we're going to get the classical action. Delta y equals 0 there, because it's the classical path. And the non-classical path, it's a squared function of delta y, so it's going to be a parabola, pretty simple for this particular example. And so the least action, they call it the principle of least action. Least action is that classical path. And the mathematics says that when you take the derivative of the action, that's that integral thing, and you set it equals 0, you get Newton's law. And it's the physics majors know what I'm talking about. I'm a chemical major, so I'd never seen this before. Okay, and the D2 star has a classical motion. I just showed you the simulation. All right, it's F equals ma, which is just that little device. And that means it has an extremum. And that's going to be important in just a second. All right, so now we're going to do some examples with numbers now. All right, we've got two examples, two different numbers. That's why I didn't put units down here. One's going to be a 1 meter unit. The other one's going to be 1 angstrom. And then this is adjusted so that it works out okay on the example. And then that's the classical path. There's non-classical paths. I can use 15 of them. I showed 3 of them here. It's going to have a constant delta y. Okay, so 15 paths. You see on the next slide, here's that same action. It's just like that parabolic, only this is half of it. So there's an action. It's units of Planck's constant. You got to divide it by h. Okay, that just makes it dimensionless. So you can put it in the exponent over here. All right, and there's the classical path. And there's the non-classical paths. Okay, pretty straightforward. Now we have to sum those paths, and if you're like me, you just shake your head, well, how do you sum that? Well, it doesn't end up being all that hard, thanks to Feynman's hints. So you write it in the Euler form there, and it's like adding vectors in a complex plane. All right, so let's take a look at what that looks like. So each dot over here has a vector. You know, there's dot number 10. There's the classical vector right there, and you add them up. And when you do that, you've got all the paths. Remember, these represent different paths. Okay, classical path and all the non-classical paths. Those represent the paths, and the ones that seem to add to the total amplitude, you can see when you get up into the higher the paths that are further away from the classical path, they don't add to the total amplitude. So there's the total amplitude. So the sum of the amplitudes is all generated by these first few paths here. And that's why the classical path is important, because it's only the paths near it that contribute to what you call observables. These are the only paths that you can find. Those are the observable paths. So remember, large action, small deviation from the classical path, it ends up being about 4 microns in a 1 meter path. That's pretty classical. And that's for a 13.6 electron volt electron. That's 2 million meters per second about. So let's do the same thing with 1 angstrom path, same velocity. You're going to have the same parabolic shape. I didn't put all the dots in here. But you get the sum of paths. It gives you 0.45 angstroms. That would give you a diameter of 0.9 angstroms. And what do I mean by that? Well, if you draw a picture, there's the real path, the free particle path, just a straight line. And these paths have the same probability, basically, as the classical path, which is, you know, that's crazy. But that's the origin of the atomic dimensions. Okay? Fairly straightforward if you follow all the arrows and all. So, small action. See that the action up here is only 1. I didn't bring it up in the other one, the action was 10 to the 10. So, small action, ill-defined path, large action, classical path. Okay, now we need one more concept. It's a stationary state requirement. It has to be a repeating amplitude in the path. This is just for example's sake. I take a deuterium or hydrogen atom, and we'll look at the classical orbit, the amplitude of the classical orbit, and let's lay it out flat so we can see it. And you put the classical orbit in there, the amplitude of it, just a sine wave, because it's a constant velocity, right? So it's just a sine wave that repeats. If it was a smaller wavelength, it would interfere with itself and disappear. So it has to be that wavelength. And all the other paths have to have that same property. All right, so here's a dramatized version of my my state. Okay, you go A, you go down to B. Let's look at A to C. That gives you can see what the path is. Every time it crosses there, it goes through the deuteron. And if we were to impose a Bornoppenheimer at this point, this is what you get. It would go back and forth, and you just get that example number 2. You get regular standard Schrodinger equation. Nothing new. But that's not what we have. We've got the electron behaving like this, and if you look at the amplitude, it's going to look something like that. You've got peaks where it goes through the deuterons, right? It's got a high momentum there. And if you want to do the whole orbit, of course, you're going to have to stretch things out and expand this all the way from A to B, and if you put it in there, it's going to look something like that. And very long path gives you very large action. In reality, it crosses the axis about 400 times. And we call it the large action gives classical life path. Okay? So our conceptual conclusion then is you've got an n, basically n equals 400 about, and it's like a very large quantum number, and that gives you a very large action. That gives you classical-like behavior. I didn't talk about the sensitivity of the action due to the potential, but you can think, remember the Lagrangian is a kinetic energy and potential energy, And so we have to, if you try to go around the nuclei, you're going to change the potential energy a lot, right? Get out of the nuclei. So that's going to change that action a lot. That gives you very classical-like behavior also. So Bornoppenheimer approximation obscures this straightforward quantum solution. The Schrödinger equation cannot easily describe this. There are ways to do it if you bring in the solid state, and it gets bad. The correlation is accessible through Feynman's wave equation over an orbital period. And the quantum mechanical correlation is defined by an extremum of the Lagrangian and action as a classically defined orbit. So yeah, the linear momentum state can be derived from basic accepted quantum principles. And if you do that, you can get an electron distribution around the deuteron, so it's something like this. Note that this scale is expanded a factor of 10. So this would actually be a very classical-like state.
Very impressed. So, questions, comments? Yes.
Very interesting work, but I have a few comments.
Sure.
First of all, Bornoppenheimer approximation may not work certain cases. So I think if you want to really rigorously compare, you have to solve a three-body Schrödinger equation instead of comparing your result with Bornoppenheimer. Now, for the three-body Schrödinger equation, there has been lots of work done last 20, 30 years, including Russian physicist Feynman, and he has developed a way to solve three-body Schrödinger equation. It's now called the Feynman equations, and I'm wondering whether you're trying to solve that equation and then compare your result. I think Bornoppenheimer may not be good comparison.
Well, you could solve it from Feynman's wave equation. You don't have to go anywhere else.
I'm saying that you can confirm your result if you have three-body Schrödinger equation solution. Then you can compare directly to it.
You can't solve it.
Feynman's approach really give the same answer. May give, but until you compare exact solution of Schrödinger equation, you're not sure whether you did it right.
All right. Well, volunteers to do that work?
Yes.
Kim's right on.
Look, I read your abstract. I noticed you said that your solution is an extremum of the action, but not a minimum.
That's
Is
right.
that right? So do you have any comments on that?
Yeah.
And then my other question is your solution a stationary state?
Yes. But it's more complicated because it has to be in the solid state because it has to involve the free electrons. The physicists out there could probably say, well, geez, the electron and the nuclei have about the same spatial distribution. That can't happen because the momentum won't align. Because the momentum space wave functions won't match up. Well, if you bring all the thousands of electrons in, you split the states, and it works out just fine. But let me show you the. I do have a. Yeah. If you look at it from another perspective, it might take way too much time.
Well, we would probably have to move very quickly on, but I would encourage more of a detailed technical discussion offline.
Okay.
That's good. We had another question.
I just wanted to confirm, what's the scale of the distance between the two deuterons? Was it very, very small at the end?
In a stationary state, at the ground state,
Yeah.
it has excited states, which allows the mechanism. At the ground state, it's around 300 Fermi.
300 Fermi.
Yeah, it's a very easy calculation to do. All you have to do is, it's a one-dimensional state, right? So you just solve the one-dimensional Schrödinger equation, for the electron through the deuteron.
So that's the revolutionary thing that you found is a bound state of these two deuterons that's much, much, much closer than the classical.
Right. For 10 years, I had to
Diatomic
assume.
atom.
Yeah, I had to assume what I call linear momentum state. I couldn't prove it, so I was going to drop the word. But fortunately, these guys encouraged me. And finally, if you look at Feynman's work, it's obvious what's going on. But until you see that.
One question that I had as chair was, as an experimentalist, I think this would imply that you'd have a preferred polarizability, atomic polarizability along the axis of the two nuclei. Is that so?
No, it's a quantum nuclei, so there is no accident, at least in the ground state. You could probably have a angular momentum state, I don't know. I'm not that much of a physicist.
I'll talk to you offline. Thank you very much. Appreciate it.
It's no longer one-dimensional when you do that, things change.
Well, that's what makes the electron wave function three-dimensional, because it can't be one-dimensional.
Unless you can find it in
The two deuterons have wave functions. We'll talk about it. Thank you. Okay. Thank you very much.